have out in front of you your geometry unit 2 review. Okay, so the beginning here starts with our conditional statement review. This for questions 1 and 2, write the converse, inverse, contrapositive of the given conditional statement. Write the biconditional if applicable. Okay, this is what we did with all the P's and Q's. Remember, we said a conditional statement, the part that comes after if is the hypothesis, and the part that comes after then is the conclusion. Okay, so I'm going to label that. The conclusion is Q, the hypothesis is P. Okay, so remember the symbolism. Okay, for your conditionals, they use the arrow to the right for all of them except the biconditional does what? What does bi mean? 2. So this one has 2 arrows. It has an arrow going both directions. Okay, so the conditional is if P, then Q. Remember, the converse switches the order. So it's if Q, then P. So when I go to write that over here, I'm going to say if it is a triangle. And you can abbreviate or do things like this. I'm going to draw a triangle instead of writing the word to make it faster. Okay, then the polygon has 3 sides. Bless you. So that would be the converse because I switched the order and I put my P back there after then, my Q up here after if. Okay, who remembers what the inverse does? Does the opposite. It negates both the P and the Q. So the order stays the same, but we add in the negation. And remember, the symbol for the negation is the tilde. So that reads not P, if not P, then not Q. So when I go to write that, I'm going to say if the polygon now make it make sense, make it grammatically correct. I can't just add the word not. I can't say if the polygon not has 3 sides. That doesn't make sense, does it? So I'm going to change the wording slightly. I'm going to say if the polygon does not have 3 sides, or you could say doesn't if you don't want to say does not. Then, okay, and again, we're negating, so it is not a triangle. So I added the not, I negated both, but I kept the order the same. So the polygon does not have 3 sides, so that's not P. Then it is not a triangle. That is not Q. All right, now what about the contrapositive? What did the contrapositive do? Well, the converse is if Q, then P. What's the contrapositive?
Well, it's like the not.
The not. Q. Yeah, it's not Q, then not P. So it negates and it switches the order. Good. So this one would read, if it is not a triangle, then polygon does not or doesn't have 3 sides. So we got our knots in there. And we did the Q first, so it is not a triangle. And then we did the knot P. The polygon does not have 3 sides. All right, what about biconditional? Who remembers what a biconditional is? We keep the order, we start with P and we end with Q, but instead of it being an if-then statement like a normal conditional, it's an if and. So that shows up in the middle of the P and the Q. So we say P if and only if Q. So we're going to say P is the polygon has 3 sides. And then we're going to have our phrase if and only if. And then we're going to have our Q. It is a triangle. So the order stayed the same. We kept P at the beginning and Q at the end, but instead of if then, we did if and only if in the middle. We can biconditionals, remember, are only true if both the conditional and the converse were true. So let's see, if a polygon has 3 sides, then it is a triangle. That's a true statement, right? I'm just going to put that out here. That's true. If it is a triangle, then a polygon has 3 sides. That's also true. So because the conditional and the converse are both true, then the biconditional is true. And they didn't ask us for the truth value, but we can determine that. And I just want to remind you that the biconditional is only true if the conditional and converse are both true. Okay, if we want to go ahead and put true or false on the others, if the polygon doesn't have 3 sides, then it's not a triangle. That's true. If the polygon, or if it is not a triangle, then it does not have 3 sides. That's also true. So in this case, all of these were true. Okay, so we're going to do the same thing with this next one. Okay, I'm going to go ahead and fill in my symbols. I know what the symbols are. All right, so there's the symbols. Those stay the same. Nothing changed there. Okay, so this time, my hypothesis, my P is the measure of an angle is 125. Okay, so that's going to be my P. My Q is, it is an obtuse angle. That's my Q. So this is a true statement. If the measure of an angle is 125 degrees, it is an obtuse angle. That is true. 125 is obtuse. Now, if I switch the order of this, if I say, if it is an obtuse angle, I'm going to do the symbol for angle. Then it measures 125 degrees. I changed the wording slightly just to make it fit better. Okay, but the concept is the same. 125 degree measure and an obtuse angle. Okay, so that's the gist of the P and the Q. Okay, so if it is an obtuse angle, then it measures 125. Is that true or false? Every obtuse angle is 125 degrees? No, this can be true, but it is not true every single instance. So we say it's false. Okay. If you have an obtuse angle, that does not mean it has to be 125 degrees. It could be, but it's not true 100% of the time, so we say false. Okay, so this time, I'm going to go ahead and come down here. I'm going to write the biconditional, but I know right now that it's going to be false. Without even writing it, I know it's false because the conditional and converse were not both true. Are y'all with me? So I'll write it. It's going to be the P if and only if Q. So it's going to say measure of an angle is 125 degrees if and only if it is an obtuse angle. I know that sounds like a true statement because you're like, yeah, if it's 125 degrees, if and only if it's an obtuse angle. It doesn't work that way. The if and only if part of that tells us it has to be able to go backward as well, which this doesn't. So that's our P, and there's our Q. So I know that that biconditional is false. All right, now I'm going to go back and fill in the inverse. That's doing the not, the negation of both your P and Q. So I would say if the measure of an angle is not 125 degrees, then it is not an obtuse angle. Okay, so I kept my P at the beginning, the measure of an angle, but I added the not. Okay, then it is an obtuse angle, but I added the not. So if a measure of an angle is not 125, then it is not an obtuse angle. That is false. If the measure is not 125, it could still be an obtuse angle, right? Could be 130, 150, anything between 90 and 180 that's not 125. It's a lot of possibilities. So that's a false statement. Now the contrapositive switches the order and negates. So it's going to say if it is not an obtuse angle, then the measure of an angle is not 125 degrees. So I moved the P to the end and added that word not. U is at the beginning. We added the word not. So if an angle is not obtuse, then it is not 125. That's true. If it's not obtuse, it cannot be 125. So remember the connection over here, we've talked about the conditional and the contrapositive are always going to have the same truth value. You see how both of them were true here? And then the converse and inverse are always going to have the same truth value. So they were both false. Okay, so make sure when you're doing, if you're asked if it's true or false, any of your statements, remember the contrapositive and conditional should match. The converse and inverse should match. They can all four match, that's fine. They can all be true or they can all be false. That would be fine as well. All right, questions about converse, inverse, contrapositive, or biconditional? You've got to know the symbols. I'll tell you right now, those symbols are on the test. Okay, you have to know which symbol, which symbolic form goes with which statement. Okay. All right, counter examples. Remember, counter examples, they counter an argument. They counter a statement. If you're countering something, you're like proving it wrong. You're saying that's not true. Okay, so a counter example is an example that proves the statement false. It proves it wrong. Okay, so the statement says no triangle has two sides of the same length. So you can either write words or you could draw a picture of a triangle that does have two sides the same length, because we're trying to prove this false. So prove it wrong is what we're doing. That's what counterexamples do. So what type of triangle has two congruent sides? Don't remember the name of it? Isosceles. Have you heard that before? Ring a bell? An isosceles triangle is one that has two congruent sides. Or an equilateral triangle has all three congruent sides. Okay, so either isosceles or equilateral would be a good counterexample. If you don't remember the words, just draw a picture and mark two of the sides congruent. There's a triangle with two congruent sides. Or instead of tick marks, you could put measures. You could put a 2 and a 2, or a 10 and a 10, or whatever you wanted to say. So either put equal measurements on them or put tick marks showing that they're congruent. Or write the word isosceles or equilateral. All of those would be correct counterexamples. It's just anything that proves the statement wrong. Number 4 says, if you live in Texas, then you live in Houston. So what's an example of somewhere you could live that's in Texas that's not Houston? A lot of possibility. I heard like 8 different answers there. I'm just going to go with Austin. Okay, you could have said Dallas. You could say League City, Webster, Galveston. Anywhere in Texas that's not Houston would be a counterexample. Number 5, if an animal has stripes, then it is a zebra. Could be a tiger, good. Could be your house cat, whatever. Any animal that has stripes would work. All figures with 4 sides are squares. Okay, so you could have a rectangle that's not a square. You could have a kite. You could have a parallelogram. You could have a trapezoid. There's lots of 4-sided shapes. 4-sided shapes are called quadrilaterals. Okay, not all quadrilaterals are squares. So any of those would be a good example. I'm going to put kite, but you could put diamond, rectangle, trapezoid, parallelogram, lots of possibilities here. If the car will not start, then it is out of gas. But the battery could be dead. Good. Okay, maybe the alternator's out. Maybe your I don't know, your starter is not working, or your spark plugs, or any of lots of possibilities would work there that would make your car not start. Okay, if 2 lines intersect, then they form right angles. So again, you can use words, bless you, or you can draw pictures. Counterexamples can be pictures. So draw an intersection of 2 lines that's not at a 90-degree angle. That's obviously not a 90-degree angle here, right? So that's a counterexample. 2 lines intersect, they form a right angle. No, they don't always. So here's an example of that. If A and B are negative, then A plus B is also negative. So if you add 2 negative numbers, it says that the sum will also be negative. Can we think of a counterexample there? Are there negative numbers that we could add that wouldn't give us a negative? Say again? I know, give me specific number. You need a counter example has to be a specific example. What do y'all think? Oh, that is not supposed to be opening. Nobody can think of one, can you? If you add two negative numbers, it just gets more negative, right? That's a true statement. So that's true. There is not a counter example. Okay. So we can't find a counter example. That means it's a true statement. All birds can fly. Penguin. A penguin cannot fly. Good. I think there's more.
Chicken.
Yeah. Ostrich, chicken. Yeah. Good. So any bird that doesn't fly would be a counter example. All right. If C and D are both integers, then the sum of C plus D is always greater than both C and D. So they're saying if you add any two numbers that are in integers, just mean no decimal or fraction. They can be positive or negative or zero, but no decimal or fraction. So thinking of any integers, if I add them together, will that always come out bigger than those numbers individually?
Yeah.
No. Go back to thinking about your negatives. If I add, let's say, -2 plus 3, what do I get? +1. Is 1 greater than 3? Is 1 greater than -2? It is, but it's not greater than both. So it says that it's always greater than both C and D. It's greater than one of them, but not the other. So this is an example that proves that statement is wrong. Does that make sense? All right, last one here. If M and N lie on a line AB, then M lies on the segment AB. So if I have a line AB, for this line to be named AB, couldn't AB be anywhere on the line? Okay, so they could be right next to each other, couldn't they? AB. So then if M and N are also on this line, does that show that M and N would be on segment AB? Because segment AB is only from A to B. It starts at A, ends at B. No, the way that I drew this, M and N are not between A and B. So this is a counter example. Okay, M and N could be, I could have drawn B down here, right? And then M and N would be in the middle, or in between, I should say. Then that would show that this is true sometimes. Okay, but this shows that it's not always true. M and N don't have to be between A and B. They could be anywhere on that line. So far, so good? Counter examples making sense? Okay. All right, let's go then back here, flip it over. We've got, let me see, I don't want to be in the middle of a proof when the bell rings. We've got 14 minutes. I'm trying to decide if we can finish this whole page. We probably can. Yeah, I'll just keep going. All right, number 13. Okay, so proofs. This is what we just finished talking about this week. Okay, this one is an algebraic proof. Okay, we've got an algebra equation that's given. Remember what we talked about when we're filling in a proof in the table, the left and right column? The first line, the statement and the reason are always what you're given. So the reason is the word given, okay? And then what I'm given, I actually write out. So I'm given that 5 times x plus 2 equals -3x minus 6. That just came from right here. I always start with my given information. Okay. I always end with what I'm asked to prove. Now that's already in there. I don't have to write it in. That one was already typed in. So that's good. But those 3 spots on your table, you should know automatically just looking at the problem. Okay, you start with your given statement, you end with your prove statement, and the first reason is just given. We don't know what the last reason is yet. Okay, so they've already filled in most of the steps. So let's see what they did here. So it looks like from statement 1 to 2, okay, the parentheses are gone. How did they do that? They distributed. Okay, so they took that 5 and distributed it in, which gave them 5x plus 10. So they've already done the work, but we have to explain the reason. So we have to say distribution or distributive property. Bless you. Okay, remember your reasons are how you got from the previous line to the current line. Okay, some people get mixed up. They're like, wait, am I filling in here how I got from 2 to 3? No, it's the previous line to the current line. What was the reason? Okay, now it doesn't have to be the immediately previous line. Sometimes it's from a few lines up, but it's how did you get the current line? What's the thing? What was used? What property or definition or postulate or theorem? Okay, so now what would be done next? If I'm trying to solve, what would I have to do to solve for x? Uh-huh. Yeah. So it tells us they want us to use the addition property. So, and we can see at the end, they have x's on the left. So we want to move the x's to the left. Okay. So the addition property is going to be adding 3x to both sides. So if you need to show that work, you can, or you can just say, okay, if I add 3x, I'm going to get 8x. And then I'll still have the plus 10. And then over here, if I add 3x, the x's will eliminate, and I'll just be left with -6. Okay, so we got from this line to here with addition.
Wait, why didn't you add the 6 to the 10?
Because if I added the 6 over, then I would have to move the x's to the right side, wouldn't I? And technically, if I was just asked to solve this, I could do it that way. But looking at how their next step, they had x's on the left. So I knew we had to move x's to the left and constants to the right. I added the 3x because it was -3x. So if you want to show the step, we can come in here and show, okay, I'm adding 3x to both sides. See, it cancels out there, and that's where 8x came from. Now then, we don't have anything else to fill in on this left side, but we can see that once we had the x's to the left, now you can see in their next step, they have all the constants to the right. So how did they move that 10 over to the other side? Yeah, they subtracted 10 on both sides. That's why it says subtraction property was used. So we added the x's to the left, then we subtracted the constants to the right. Then what was done? How did we go from 8x to just x? We divided by 8. Good. So that's the division property. Of equality. You can just put division property. Y'all following? Does that make sense? Now you're not going to have to hand write things into your proofs on the test. It will be, if there's blanks like this, there will be choices. It'll be like a drag and drop, and you're going to plug in which rule goes here, here, and like which step goes here, here. Okay. You don't have to just come up with it out of nothing. There will be some choices up there, and you'll have to figure out.
And there be like, right.
Well, the way that you did this solving, you could have done it a different way, but there's only one correct answer on these because of the way they had stuff already filled in. But like I said, instead of adding the x's to the left, we could have subtracted the x's to the right and then added the constants to the left. And then we would have divided by a negative, and then we would have done the symmetric property to flip it back around to get the x on the left. So we could have done that, but the way they had stuff already filled in, these were the only correct answers. All right, so here's another algebraic proof. So we start with our given information always. Okay, so they've already typed, oops, that was supposed to be a highlighter. They've already typed in the actual statement, but what's my reason going to be? Given. Okay, so I'm going to write given. And then the last line, the last statement should always be what you're trying to prove. So we can go ahead and fill that in with x equals 21. So now the only thing we have to fill in for reasons is how we got from line or statement 1 to statement 2. How did we get from here to here? How did they get rid of that divided by 2? They multiplied by 2. So that's the multiplication property. They multiplied both sides. What you do to one side, you do to the other. Okay, if you want to show them multiplying, you could do that. You could see that they're multiplying by 2 on both sides to eliminate that denominator of 2. So then you're left with just the numerator, x plus 3, and then 12 times 2 is 24. And then you can see they subtracted 3 from both sides to get 21. They already wrote subtraction property. All right, 15 asks for the difference in postulates and theorems. Does anybody remember? We talked about it in the notes again yesterday. It's been in 2 or 3 of our sets of notes because I told you it's going to be on the test. You have to know the difference. Postulates don't require proof. That's exactly right. Why that highlighting keeps appearing. Okay, so postulates don't require proof. Theorems require proof or can be proven, however you want to word that. Okay, we've got to know the difference in postulate and theorem. All right, here are the 4 parts of Euclidean geometry. There's postulates and theorems, which we just talked about. There's defined terms and there's undefined terms. We have to know the order that those go in, and that's in our notes also. And we did it in our practice also. Okay, so the basis of geometry, what was the first thing we learned? The first 3 terms we talked about in Unit 1. The 3 undefined terms, which were what? Don't remember what they were? Not asking that in this problem. I just want to know if you remember. The 3 undefined terms are points, lines, and planes. Because there's a point is just a location. Lines and planes can't be measured. They have no size. They go on forever. Okay, there's no formal definition. So that's the basis of it, are those 3 undefined terms. That's first. Then what? Then we get defined terms. We have formal definitions. Then what? Ooh, I heard 2 different ones. What do y'all think? It's postulates. Okay, because postulates don't have to be proven. They're accepted as true. And then theorems require proof. And those theorems, we can prove them using all of this stuff. We can prove them using postulates and using definitions. Okay. So theorems use everything under behind them in the order. Does that make sense? Okay. See. All right, yeah, we'll stop there. So that was algebraic proofs and then the Euclidean geometry stuff. So if you have questions on 17 on, I'll be making additional videos. You can go watch the other videos if you need help with your geometric proofs or the later stuff in the review. When is the review due? Tomorrow, Friday, test day.
Can we make it like a Thursday? Friday's supposed to be like